Okay, so let's wait for a couple of minutes. Okay, so hello everyone, and I welcome you all to this interaction session. So this interaction session is of week 2 assignment. So here we will try to solve these problems related to week 2 assignment. Not directly solve the week 2 problems, but we will try to solve some other problems that will indirectly help you to solve the assignments of week 2. Okay. So once again, let's wait for a couple of minutes so that other people can join also. Uh, what I noticed in week 2 assignments that all the questions are from basically BCS theory, and mostly the problems are from BCS theory. And so I will start with the BCS theory and will solve some problems related to this BCS theory. And if I get some time, then I will try to discuss some other topics too. Okay, so that being said, let's start this interaction session, and let me share my screen. So, uh, okay, so Samina, you have shared some file file link. I mean, what is? Can I know what is this? Okay, anyway, let's start with our first problem. So, in the last interactive session also, one student asked me to explain this, that how this Cooper pairs basically occurs in a superconductor and what is the physical interpretation of that. So I will address this problem once again so that you can become more familiar to this physical interpretation of Cooper pair. And because this thing is basically the base of this BCS theory. Okay, so it's very necessary to properly understand what is happening when there is two electrons and they are forming a Cooper pair. Okay, so let's start with the physical interpretation. Physical interpretation. Of Cooper pair. Okay, so this is a problem number one. So as you all know, that the superconductivity generally occurs in very low temperature in conventional superconductor, though there are some high TC superconductors discovered these days, but generally in BCS theory that works in the conventional superconductors, and that happens in very low temperature. So all the discussion that I will do here is basically very low temperature, and specifically T is at 0 Kelvin. So ideally, all this discussion will be made at T is equal to 0 Kelvin. Okay. Uh, so let's start with the physical interpretation of Cooper pair. Okay. So to start with, let us assume a lattice, and let's say there are four ions, ion A, B, C, and D. So normally they are in their I mean equilibrium position, and at this position the total lattice is charge neutral. There is no like polarity, charge polarity in the lattice present. Now say, let's say there is an electron that comes toward these ions, and due to this electrostatic Coulomb interaction, these positive ions, they get attracted to these electrons and they get displaced from their neutral position, and so basically there is a deformation in the lattice and a polarization appears in the lattice. So this plus charge, they gets deviated from their neutral position, they gets deviated toward this side, and so basically there is a net positive charge now appears here due to this approach of this electron. Okay, now let's say this electron passes through this lattice, passes through this lattice in this direction. Okay, and but it's still near this lattice, so the deformation is still there. So the time scale is, let's say, very small, and this small time scale, the electrons cannot get time to go back to their neutral position. Okay, so in this small time scale, you can see that this deformation is still present there. Okay, and due to this deformation, there is a positive net positive charge here, and due to this net positive charge, another electron that is nearby to this lattice point, it get attracts toward these positive ions. Okay, so the second electron, one electron goes through these lattice points and it's now here. Now another electron comes, and these electrons also get attracted toward these positive ions. Because there is a deviation from this neutral point, there is a net positive charge here, and this positive charge attracts these electrons also, and in this way these two electrons, they kind of gets coupled to each other through the interaction of this lattice vibration basically. And as we all know that this lattice vibration can be called as phonons, or is called phonons. Okay, so this is how by interacting through the phonons, two electrons, they get coupled to each other. Okay, so and these two electrons are called Cooper pairs. So this is how we can physically understand how a Cooper pair generally get basically how these Cooper pairs get created in this lattice using this interaction of this phonon. Okay. Okay, so this is the physical picture, and this total event, that it can also be represented to a Fermi to this Feynman diagram. Sorry, so this total event, this event can be also represented using this Feynman diagram, and this is basically someone's mic is on. Can you please mute it? Okay, so anyway, so this is how this interaction. So basically, this is one electron with momentum k and spin up. So this electron goes and scattered from these phonons. The phonon's energy is represented using this h bar omega d. So this is basically the Debye frequency, and this is the energy of the phonons. Okay, so this electron get scattered from this phonon, and then its momentum gets changed to k prime, and but its spin is same. Okay, so it gets scattered to this state, and this another electron, the pair of, so there is in Cooper pair there is two electrons. So one electron gets scattered from this way, from k plus positive to k prime positive state, and the other electron gets scattered like minus k negative to minus k negative state. Okay, k prime negative state. Okay, so this is basically the spin direction, and this is the momentum. Okay, and this is the phonon. Okay, so now we can also understand this using this this diagram, where f is the basically probability of, this is basically the Fermi-Dirac distribution function. And what this represents the probability of an electron state, single electron state basically. So of an electron state to be occupied. Okay. Now this is the Fermi-Dirac distribution function, and we all these representations are being made at this to 0 Kelvin. Okay, so this is a very important thing, and we have to keep this thing in mind while making these diagrams or these explanations. Okay, now below this E is equal to EF, this is the Fermi energy. And as we all know that below the Fermi energy at 0 Kelvin temperature, this every electron state is basically occupied. That is why the Fermi energy distribution function is basically 1. 1 means all the states are occupied below E is equal to EF. Okay. So this is the case in normal metal. When this is not a superconductor yet. Okay. Now, as soon as this becomes superconductor, in the case of in the case of a superconductor, what happens that basically the electrons interact with the phonons, and the phonons have an energy of h cut omega d. Okay. Now this energy, because every state here is filled, so the electrons in the states. So the electrons in this state cannot jump using this h cut omega d energy, because as you can see, this state is also filled, and if it absorbs this energy also, the above state here it's also filled. Okay, so there is no way this electron can jump here. Okay, so all these electron states here are completely filled, and that is why these electrons cannot interact with the phonon. Okay, the electrons that can interact with the phonon is only in the h cut omega d range below the Fermi energy in this portion. So in this portion, the electrons have because these states are not filled, these are basically empty states. So these electrons have the opportunity to absorb the energy of the phonon and to scatter to these states. And this is what occurs when a Cooper pair is formed in the superconductor. And this is why in the case of a superconductor, you will see later that the Fermi distribution function is not ideally like the normal metal. So as soon as this energy range approaches the Fermi energy, you can see that there is a reduction in the probability. So there are some free state generates here. So these states are now free, empty states basically, and some states are then occupied above the Fermi energy also. Okay, so now the probability, basically the Vk, or the Fermi energy, Fermi Dirac distribution function, that get evolved to this form of function. Okay, so also you can say, using this Fermi sphere, you can see that if this is the Fermi energy, this is the E is equal to EF level. So below the Fermi energy, only in a h cut omega d distance, these electrons in this region, can only jump to the above empty states, absorbing this energy h cut omega t. Okay. Now so the electrons can now jump to this region, and the width, so this is basically of width h cut omega t, and it can now jump in here also, and the highest level it can jump is if it jumps from here and then absorbs the energy of h cut omega d, and it then lands up here. Okay, this total range is to h cut omega t, because this is also omega t and this is also h cut omega t. So this total width is to h cut omega t, and this is a very important result, as we will see later. So this is all the discussion I had to complete on these Cooper pairs, and that ends our discussion on question number 1. Okay, so if you have any problem or any question, then you can ask here. And now I jump to question number 2. So as you know that in the case of a Cooper pair, the total momentum, so one electron, if this is a Cooper pair, say this is one electron and this is another electron, and this forms a Cooper pair, then this electron, if this electron have a momentum k and spin up, then this electron must have a momentum k and spin down. That means their total spin, this k, let's say this is k equal to the total spin, total angle, total momentum. So this is also 0, and total spin because this is up and this is down, it cancels each other, and this is also 0. So the problem is how can one explain this zero momentum state of Cooper pairs? Okay. So why the net momentum of these two electrons has to be 0? Okay. So the net momentum of this electron has to be 0. And what is the reason behind that? If one electron have k positive, then another electron must be minus k. Okay. So that they are equal in amplitude but opposite in sign. Okay. So this is positive, this is negative, and the total k is 0. Now, what is the reason behind that? So let's again start with the Fermi sphere. Okay. So let's say one electron have a Fermi sphere this, and another electron. So let's say the total, let's say the center of mass of the momentum, that is k plus minus k. So that ideally should be 0. But let's imagine a situation where this Kcm is not equal to 0. Okay. So that the Fermi sphere of the two electrons, they are not concentric. Okay. So let's say this is the for k1 and this is for k2, and they are not concentric. So if they are concentric, let's say this Fermi sphere of electron 1 and the Fermi sphere of electron 2 is also here, then you can see that the the center of mass of this momentum is 0. But let's say a situation where this center of mass of electron 1, this Fermi sphere of electron 1 and the Fermi sphere of electron 2, they are separated from each other. Now we can see that the electrons only in this region, only they can jump from here to the outside, because all the internal states are completely filled. There is no space for the electrons to jump. So only the electrons near this Fermi sphere, the Fermi energy basically, they can jump outside, because these are empty states. So they jump outside, absorbing the energy of the photon, that is h cut omega t. Now when the Fermi sphere of these two electrons, they are not coinciding with each other, you can see that the electrons only this region, only in these two regions, the electrons can get scattered. Okay. In all the other regions, let's say that if we consider a region electron here, okay, then it cannot get scattered, because this is 1 and now this is k2. Okay. But so this is k1, and now we can see that this electron in this region cannot get scattered with an electron in this region, because they are totally separated. Okay. So only these electrons in this region, they can scatter with each other using a phonon. Basically they can form this Feynman diagram. Okay. So now if we see that in the case of a superconductor, in the density of state, there is a gap appears at the Fermi energy. Now because there is no single electrons here, from here we can say that all the electrons, they have to be scattered with this phonon, with absorbing this phononic energy from this region. Okay. So that for that to happen, I think for the maximum electron to get scattered from each other using this to get scattered from one phonon, this region has to be maximized, because otherwise if these two spheres are totally separated, only this portion of electron, they have the similar kind of momentum, and they only can get scattered from each other. using a phonon. Okay, but when this so now for this region to be maximized, how can these two region can be maximized? If we bring these two sphere closer to one another, okay, let's say now they are closer, you can see that this region gets increased. So now the electrons have more momentum space to form a copper pair. Okay, and when these two spheres are totally coincided with each other, now we can see that all the space, in all the momentum space, the electrons have the freedom to get scattered and from a phonon and to make a copper pair. So that is why when these two spheres are coincided to each other, I mean when Cm is equal to 0, in that case only all the electrons, they can near the Fermi energy, they can make a copper pair, and then only this band gap, this gap in the Fermi, this gap in the density of state can appear. That is one way to understand why this center of mass of the electrons in a copper pair, they must have to be 0, so that I mean the maximum number of electrons in the near the Fermi energy, they can form a copper pair. The momentum space freedom of this electrons is maximized when this Kcm is 0 for the electrons. Okay. Okay, so let's go to question number 3 now. Now, the question number 3. So, the question number 3 is, how can we explain the total spin of this Cooper pair to be 0? So the total spin of this Cooper pair to be 0. Okay, before that, has anyone any question? Am I audible to everyone? Can you please type in the chat box if yes? And if you have any question, you can also type in the chat box here. Okay. So, am I audible or not? Okay, thank you, Mercy. Okay, so let's now proceed to explain why the spin of one, if in a Cooper pair. Let's now explain that if in a Cooper pair, let's say this is one electron and this is another electron. So if one electron has spin up, in the other electron then must have spin down. Why this happens? What is the reason behind this? Okay, so let's try to explain that now. Okay. So as we have explained right now that Kcm, I mean the total momentum K1 plus K2 for a Cooper pair is 0. Okay, and this 0 momentum state resembles to S wave state. Okay, so what is the S wave state? So S wave state basically means that, let's say for a hydrogen atom, the angular momentum is represented with S, P, D, F, etc. Right? Now for S, we know that L is equal to 0. So the angular momentum for this Cooper pair, so that is also 0, and that is why this superconductive state, Cooper pair state, is also called a S wave state. Okay. So this state is basically symmetric. As you may know that for the 3D hydrogen atom, if we plot this S orbital, we can see that it's a totally sphere. So there's no asymmetry in the orbital. Okay, so the spatial part of the wave function, that is symmetric. Now let us just write the total wave function of this Cooper pair. Okay, so the total wave function of this Cooper pair can be written as k1 k2 sigma 1. Sigma represent the spins of the two electrons. Okay, so this can be written as psi of k1 k2 sigma sigma 1 sigma. So this is the spatial part and this is the spin part. Okay, one second. Okay, so as you have already seen that the so this is the spatial part, this is the spin part, and as k is equal to 0 for a Cooper pair, so this part is symmetric. And as we know that for it to satisfy the Pauli exclusion principle, this total wave function must have to be asymmetric. Okay. Now, for it to be asymmetric, one part of these two must has to be asymmetric, and as this one is symmetric, so the spin part is must to be asymmetric. Now, how can we represent the asymmetric spin part? So this can be represented at this chi of, let's say this is for electron 1, chi 1 of sigma 1, chi 2 of sigma 2 minus chi 1 of sigma 2, chi 1 sigma 1 plus chi 2. So as you can see that this is asymmetric on the interchange of the spin. If we replace chi 1 by chi 2 and chi 2 by chi 1, sorry, sigma 1 by sigma 2 and sigma 2 by sigma 1, we can say that you can easily verify that sigma 1 sigma 2 is equal to minus chi of sigma 2 sigma 1. This means that the spin part is now asymmetric. Okay, and okay, so now we have arrived to the conclusion that the spin part of the wave function, spin part of the wave function for these Cooper pairs, they are asymmetric. Okay, now let's try to derive the scattering matrix for a Cooper pair. Okay, so let's say this is the scattering matrix. Okay, and this is the scattering potential. Basically, we can assume that this is the attractive potential that binds these two electrons in a Cooper pair. Okay, now the scattering part, scattering matrix, we will see that how this. One second. So we will calculate the scattering matrix right now. Okay, so this thing can be expressed as this psi star. Now k1 k2 prime sigma 1 sigma 2 ak k prime. So how this scattering occurs? This potential is basically momentum dependent potential. There is no spin dependency of this potential. So the momentum of these electrons, they get only changed in this scattering. Okay, so the initial momentum, if the initial momentum of the two electrons in the Cooper pair is k1 and k2, then after scattering they become k1 prime and k2 prime. Now let's calculate what is the actual expression of this. Okay, psi star. Now we will break it up to these two parts, q1 prime, k2 prime, and then psi k1, k2, psi k prime. Because we can break this part into spin dependent part and space dependent part, so we only take the space dependent part to here, and then we write the spin dependent part here. So chi1 star sigma 1, chi2 star sigma 2, chi1 star sigma 2, chi2 star sigma 1. This comes from this part, this goes here, and now this part goes here. So this multiply by chi1 sigma 1, chi2 sigma 2 minus chi1 sigma 2, chi2 sigma. Okay, so I think it's clear up to this part. So we just basically splitted these two wave function, and we took the space dependent part here from this wave function and the space dependent part here from this wave function. This v is here. Now the spin dependent part, I have written that explicitly. This is the explicit form of the spin dependent part from this wave function, and this is the explicit part from the spin dependent form from this wave function. Okay, and this total is the wave function of a Cooper pair. This one is the wave function of a Cooper pair, and this is also a function of a Cooper pair, and this is the scattering potential. Now let's calculate this explicitly, and so this gives, if we calculate this explicitly, this will give you psi of k1 prime, k2 prime, psi k prime, psi of k1, k2. This part will give you this part will give you chi1 sigma 1 square, chi2 sigma 2 square, then this will be multiplied plus chi1 sigma 2 square, chi2 sigma 1 mod square. So this is one part, okay, and that part will be chi1 star sigma 1, chi2 star sigma 2, chi1 sigma 2, chi2 sigma 1 minus plus chi1 sigma 2, chi2 star sigma 1, chi1 sigma 1, chi2 sigma 2. So if you calculate this multiplication carefully, you will get this, okay. And from here, if you see that if sigma 1 is equal to sigma 2, if the spins of these electrons, okay, so we know that the spin of electron has spin half, okay. Now this spin half can two component, Z basically have two component, plus half or minus half. Now say electron 1 has plus half, or electron 2 has plus half. Similarly, also electron 1 can have plus half, electron 2 can have minus half. Basically, we can generally express that this spin of this electron 1, they can either be is equal to electron spin of this electron 2, or spin of this electron 1 can be opposite to spin of electron 2, because they can also only be plus half or minus half, right? So either they can both be plus half or they can both be minus half, then the spin of these two electrons are equal, or spin of one electron can be plus half and the spin of other electron can be minus half, or then this can be represented as spin of electron 1 is negative of spin of electron 2. Now we can, okay, so let's go to this. Okay, now we can take these two conditions separately. Now when spin of one electron and spin of the second electron, they are same. Basically when sigma 2 is equal to sigma 1, we can see that from expression this term and this term, they are equal, exactly equal. Okay, so you can put it and check here, check from this expression. So you can put sigma 1 and sigma 2, they are equal, and you can put a general term of sigma, let's say they are equal to sigma. So in the place of sigma 1 and sigma 2, you can just put sigma. Also here you can just put sigma, and we can see that you can check that this term and these terms, they get exactly the same and they cancel each other. Okay, and that is why this term goes to 0 when sigma 1 is equal to sigma 2. So basically there is no scattering that can be possible when sigma 1 is equal to sigma 2. No scattering is possible. So if both electrons are spin up or spin down, I mean the spin of these electrons are equal, they are same, there can be no scattering. So scattering matrix is equal to scattering is 0. So the only condition that is left is sigma of electron 1, I mean the spin of electron 1, that is minus of spin of electron 2. That means if sigma 1 is plus half, then sigma 2 is equal to minus half, or if sigma 1 is minus half, then sigma 2 is equal to plus. Okay. So if one spin is up, the other spin is down, and if one spin is down, the other spin is up. So that is why we can say that if S1 is half and S2 is minus half, then what is the total spin? S1 plus S2, that is 0. Okay. Similarly, if S1 is equal to minus half, S2 is equal to plus half, because these two are only possible for this scattering matrix to be non-zero. For this to be non-zero, the only conditions that are left are these two. And in both this case, you can see that H1 plus H2, the total spin is 0. That is why we take this spin of these Cooper pairs, they are exactly opposite to each other. If one spin is up, if one is k, momentum k and spin up, then the other is momentum down, spin down. So this is how the total spin of a Cooper pair that becomes 0. So this is the end of question number 3, and now I will proceed to question number 4. Before that, if you have any question, then please ask. Okay, so if there is no question, let's proceed with question number 4. The question number 4 is how this Cooper pair now can be explained mathematically using the basic, very general formalism of two electrons. Using the Schrodinger equation for two electrons that are connected with an attractive potential. Okay. So if there are two electrons, electron 1 and electron 2, and they are interacting with each other using an attractive potential. So using an attractive potential V naught, say V is equal to minus V naught. The negative sign shows that this is attractive. Okay. So if these two electrons are interacting with each other using this attractive potential, then how can these two electrons form a Cooper pair? Okay. So let's say, so that is the question here. So the question is, explain formation of a Cooper pair using two electron Schrodinger equation. So let's try to answer that. Okay, so let's first consider a Cooper, what is Schrodinger equation for two electron system. Okay, so for the two electron system, the Schrodinger equation is written as this. This is the potential through which the electrons are interacting with each other, and let's say this is the total wave function R1, R2, and let's say this is the energy of the system. So this is the time independent Schrodinger equation for a two electron system. Okay, and now to deal with this equation, it is better to go to the to transfer the coordinate to the center of mass coordinate. Okay, so now we are using the coordinate of electron 1 and electron 2. So it will be easier to work with this equation if we transform this coordinate system of electron 1 and electron 2 to another coordinate system which uses the center of mass of these two electrons. Okay, so the center of mass coordinate of these two electrons. Now how can it be written in that transformed coordinate system? So let's say now after transferring the coordinate, now the coordinates are r1 is r, that is r1 minus r2. So the position of one electron with respect to another electron, and another coordinate is r is equal to r1 plus r2 by 2. Okay, so this is the center of mass coordinate, and this is the relative coordinate of electron 1 with respect to electron 2 with respect to electron 2. Okay, now in these two coordinate system we can write this Schrodinger equation in this form. Okay, so minus h cut square by 2m sigma r square, this is now the relative coordinate, and minus h cut square by 2m. So this is the center of mass coordinate and this is the relative coordinate. Okay, one thing to notice here is that this potential is not spin dependent potential. This is totally spin independent potential, and this is basically a space dependent potential. So this is a space dependent potential. And one thing to notice here is that, sorry, there is a little bit mistake here. So now this m also gets changed. Okay, so in the case of relative coordinate, it goes to mu. This is called the reduced mass, and this is the effective mass. Okay, so this reduced mass can be written in terms of the one electron mass. So the reduced mass is half of one electron mass, and this effective mass is 2m. So this is the total mass of the electron system. So this is now the okay. So now this is the Schrodinger's equation in this transformed coordinate system, where this is the relative coordinate, and this is the center of mass coordinate, and this is the reduced mass, and this is the total mass. Now we'll try to solve this equation. Okay, so the thing we noticed here is that v is not dependent on spin. Okay, also this v does not depend on r, because v is only a function of small r. This is the relative coordinate. So v is not a function of this r, which is at center of mass coordinate. That is why we can say that the wave function is phi of r1 comma r2. If we write it in terms of this transformed coordinate now, that is r comma r. Now we can write this term as psi of r1 complicated or on involved expression of psi that is only dependent on r, because v is dependent on r, and this v makes this equation complicated. Okay, so one term that is dependent on, that comes due to this v, and that is dependent on this relative coordinate, and another term that is totally like free particle, free electron wave function. Okay, because as this v is not dependent on this r, so if we neglect this term, then we can see that this term only gives you like a free electron wave function Schrodinger equation. Okay, so that is why this term only r dependency in this psi comes in this term. Okay, so now if we put this term here, so if we put this term here, we get that minus h square by 2 mu by psi r square plus v of r. This term when in acts on this one, so we put this term in place of psi of r1 and r2, and if we calculate then the rest of the thing, you will get the simplified equation like this. Now here this E tilde is basically this E minus h cut square by k square by 2m star, where k is the center of mass momentum. Okay, that is k1 plus k2, and we know that for a Cooper pair the center of mass coordinate is 0, so E tilde is basically is equal to E. Okay, so now this equation gets simplifies to this form, h cut square by 2 mu grad r square plus vr acting on psi, that gives E of psi. Okay, so this is the final two electron system Schrodinger equation. Okay, now we will proceed with this equation in our hand. So the equation is minus h cut square by 2 mu psi r square plus v of r acting on psi r, that gives you E of psi r. Okay, now to solve this equation we will use this Fourier transform, so that in the Fourier space this equation get more simplified. Okay, so the Fourier transform, using the Fourier transform you can write psi of k, that is equal to psi of r to the power minus I dq r, psi of r, that is equal to okay, so this is basically the Fourier transformation relation of psi. Now we substitute this form of psi r here in this equation. If we substitute and calculate, okay, I will not do this explicitly, but one can verify. If you can also, there is another relation of, we can also Fourier transform this equation. So we can write this Fourier transform on this term. So Q is the momentum and E of Q. Okay, so this is the Fourier transform relation of this potential. Now if we substitute these two terms in this equation and we simplify this equation, then we can get, I will not do this explicitly, but you will get that h cut square by k square by 2m 2 mu psi k after Fourier transformation and simplification. So this becomes 2 pi to the power E of k minus k. there is a similar equation. There is a similar equation in the assignments, and that is why I am not doing the exactly the total detailed calculation, because that will be directly solving your assignment. So I will not do that. So I will basically jump some steps, and I will leave the steps to for you to do. Okay, so do the in between steps, and I'll just showing some results. Okay, then dq bar, and this becomes psi of k. So after substituting these forms here and doing some simplification using this integration by parts, you can arrive at this equation. Okay. Or from here we can write that t cube of k prime by 2 pi. So this is a very important equation. So arrive at this equation. Now here mu is, as you know, mu is m by 2. So let's put it here, and we get that if you put it here, then this gives you 2 h cut square k square by 2m. So 2 h cut square k square by 2m we can replace as E of k. E is equal to h cut square k square by 2m. This is the energy of a free electron. Okay. So this is the energy of a free electron, and that is the energy of a free electron, and we put it here and give the simplified equation like this. Okay. So this is the final equation. So up to now we have not used this explicit form of this V. So the next goal will be to use the explicit form of this V and to analytically solve this equation. Okay. Now let's say the electrons are, so in the Cooper pair the electrons, I have already told you that the electrons are coupled with each other with an attractive potential, and so let us express this k, V of k minus k prime, in terms of that potential, attractive potential. So minus sign gives you the minus sign tells you that this potential is attractive, and V naught is some constant value of that potential. Okay. So V k minus k prime is minus V naught when these electrons are very close to the Fermi energy. That means if psi k is the electron's energy and this is the Fermi energy, then mod of psi k minus psi f, sorry, mod of epsilon k minus epsilon a, that must be h cut omega t. Okay. So E minus EF must have to be less than h cut omega t, because as we know that if this is the Fermi energy, then electrons only in this region they can jump outside. Okay. So the electrons that can form the Cooper pair, they exist or they resides only nearby this Fermi energy level, and if this electron has an energy epsilon k, then this width is h cut omega t. So from here we can see that Ek minus Ef, when this Ek minus Ef is less than equal to h cut omega t, when this energy of this electron is only in this range, then only they can form a Cooper pair. That means they feels this attractive potential minus V naught. Okay, so the condition is this. Otherwise, this potential is 0. So now we get the explicit form of this potential. Okay, we can put now this to this expression, and let's put it. So if we put this thing in the expression, we will get that. So this is minus p naught. Okay, so let's replace this by minus p naught. So let's use the same notation. This is express it by ek only, so that there is no confusion. Okay. Mm. So this is the term, and so this is the actual equation that we have to solve now. So our ultimate goal is to find goal is to find the gap equation by solving this thing. Okay. So the gap, if we can find the gap, that means that there certainly there is some Cooper pair that existed in the system, and that means the system is superconductor. Okay. So that is why our goal will be to solve to get the approximate expression of this gap. Okay. So this gap in the Fermi, if we again go to this density of state form, so this gap delta, we will find an explicit expression of this gap from this equation. Okay, we'll try to find. Now okay, so okay, so now we will take an approximate. We will define what is psi. What is this band gap? Okay, delta. What is this gap? This is not a band gap, but this is the gap in the Fermi relation that appears. So we will define this gap as this is a function of k. So as e minus 2 ek. This term basically star psi k. So we will define this as this. So if we now substitute this in this equation, then it gives minus v naught into, so this psi k prime is delta of k prime by e minus 2 epsilon k prime. Okay, and also there is the v naught term, and so this term goes to basically psi of k. This is not k prime. So this term goes to psi of k using this equation. Now if we simplify this equation again, so I will again not do the explicit states, but you can see that okay, so you can see that if you solve for this delta, okay, so delta is basically appearing in both sides of this equation. So we will use this term. So del k. So this was our equation. Okay, I'm sorry for the interruption. Let's join again. Okay, so let's continue with that. Sorry for that interruption, and let us just continue this discussion. Okay, so we are solving this equation. Now, what we will do, that from the knowledge of Ponnett's method theory, you know that we can write this term delta q k prime by 2 pi q. That can be written as gk of k, and that is also equal to g of k. So we can write intensity of state form. Okay. Now, we know that the electron only resides near the Fermi energy. Okay. So we can write this term in this form. So delta q k prime by 2 pi q. We can write this as approximately from EF to only EF plus h cut omega t, because we know that only electrons that residing, yeah, so we know that electrons that are only residing in this area, that only is we are considering only the electrons in this region only. Okay, because only electrons residing only in this region, they can only contribute to the superconductivity. So we will do our integration from EF, that is the Fermi energy, to this energy range only. Okay, so here h cut omega t is the energy of a photon. Okay, and if we now express this in this form, so we are now doing this we are now doing this integration only up to this energy range. So this is g of epsilon time t epsilon. Okay, now this g is basically density of states. So now we know that this h cut omega t, so this h cut omega t is very less than the Fermi energy. Okay, so all the in all the region that we are considering here, this density of state can be approximately written or replaced with the density of state in the region of Fermi energy only. So we can replace that with this, because h cut omega t, because of this condition. So this basically gives us g of h cut omega t. So this is how we can write this. We can write this term in terms of this density of state at Fermi energy times this energy of this phonon. So if you now put this or substitute this in this equation, we will get the form like, so we already replace this thing with this term, so it gives us what is the problem. PowerPoint is not responding, so we have to close it again and then start it. So let's close the presentation. And let's start it again. Okay, so we are here, and so I think it's visible now. Let's close it and let's start with this thing. Okay, so we are solving for this term, so we can replace it now with g of EF times h cut omega d, and now we can also replace everything that was a delta k prime by e minus 2a k prime, that is equal to delta k. Yes, because
Your slides are not visible. Actually, I think your screen is not shared. I think.
okay. Thank you. Yeah. Okay. Sorry. So now I think it's visible, and so we are here. We replace the integration term like d cube k prime by 2 pi cube with this term. This is the density of state at Fermi energy and this phononic energy. Okay? So we replaced with this term and with this, and because this is the approximation we made here, is this h cut omega t, this is very less than EF. Okay, so the entire range is very near to this Fermi energy. If this is the Fermi energy and this is Fe, then we are working very near to this Fermi energy, because this range h cut omega t, that is very small to this EF compared to this EF. So we are working very close to this Fermi energy, and that is why we can replace the density of state GE with this density of state at the Fermi energy. Okay, now I will not again do this total. So this is the Fermi energy range. So this is the range at where the electron can get excited only. So we are working in this range only, because electrons residing only in this range can excited to upper energy state. All the below states are filled totally. Okay, so now you will not you can calculate this again, this expression explicitly, because this is your assignment problem. So I will just write the final result. You can do this calculation by yourself and you can verify. The final result gives you this energy E. So this final result gives you that this energy E can be written as this. Okay. V naught. Okay, so you can solving this equation, you can reach to this equation, and in this equation, this is a very important equation, and this is called the BCS gap equation. Because this is not actually exactly the BCS gap equation, but from here you can reach to this gap equation. But how? Because this term is your free electron. I mean, so the energy of free electron. If you consider 2 electron near this Fermi energy, okay, so then the energy of this 2 electron is this. Now, if this when these 2 electrons are free, then only this works. Now, let's say there is a attractive potential, and these electrons, this electron 1 and electron 2, they interact with each other using this attractive potential, and that in turn gives rise to this Cooper pair. Okay. So when we don't consider this attractive interactive potential, I mean when V naught is 0, you can put V naught is 0 here, and you see that this term vanishes. So when there is no interactive attractive potential, these two electrons act as free electrons, and the total energy is given by this, as you know. Now whenever there is an attractive potential V naught, these electrons get reduced, this energy get reduced, sorry, and so this energy get reduced by this amount of energy. Okay, and that is why this is called the binding energy. So this energy gives stability to these electrons to make a Cooper pair. Okay, so as you see that whenever this attractive potential appears, the energy of this electron get reduced because of this term. So this is called the binding energy, and as you will see later, this binding energy, this is totally equal to this gap. Okay, so the energy gap that appears at the Fermi energy, that you can derive later, and you can verify that this gap and this term, they are totally equal. Okay, so this gap appears in the superconductor, and that is how the energy of this Cooper pair that get reduced, and so the Cooper pair state basically get stabilized because the energy of this Cooper pair state is lower than this free energy level. Okay, so that is how Cooper pair is formed, and we now see that this using only this two electron system, very simple two electron Schrodinger equation, we can arrive at this equation. Okay, if we explicitly consider the form of V like this, if we explicitly consider the form of this potential V k minus k prime as V naught, whenever these electrons are very near to this Fermi energy and they satisfy this condition, then there appears an attractive potential, and that can be replaced by this, and otherwise it is 0. So when we put this form of this attractive potential in the Schrodinger equation, we started with the Schrodinger equation like this. So we started with the Schrodinger equation like this. Then we made a Fourier transformation of this equation, and we arrived at this equation. Okay. So by doing the Fourier transformation, you can get this equation, and now when in place of this Vkk prime, you can put this equation, this form of this Vkk prime, and then by solving this equation, we can get to this ultimately you can get to this equation where you can get this form of this Fermi energy, that is you can get the form of this binding energy, and you can also later verify that this binding energy is in turn equal to this gap. Okay, so gap in the Fermi energy that appears. So this is a very important equation, and with this we reached to the end of this question number 4. Now we will try to advance with question number 5, and if you have any question in between, you can just ask me now, because now I will start with this explicit derivation of BCS theory. Okay, so to start with, so question number 5 is explicitly means quantum mechanically, totally purely quantum mechanically. Derivation of BCS theory. So again, I will not do everything. I will basically do very small portion, but I will just represent the. I will just write the very important results of this BCS theory and how we can go to these results starting from the initial, starting from this initial Hamiltonians, etc. Okay, so I will not do the explicit calculation. I will just give you a flavor of the results from this BCS theory. Okay, so we will basically use the second quantization here. The second quantization deals with annihilation and creation of particles in a state, in a quantum state. Okay. So let's say there is a quantum state psi which has particles n1, n2, etc. Okay, in I. So let's say that we have a wave function, and this wave function is represented like this, and this wave function says that in the state n1, in the state 1 there is n1 number of particles, in the state 2 there is n2 number of particles, and the total wave function is written by this equation, by this term. Okay, psi. Now if we, okay, so the second quantization says that if we apply a creation operator, so that is written by psi. So let's say initially in the state psi, in the state I, there is zero number of particle. Okay. Now if we, so this is the creation operator. And now if we apply this creation operator on this state, on this wave function, so it will generate a particle at the ith quantum state. Okay. So if there was initially zero particle here, so now after applying this, creation operator, so there will be one particle at the ith state. So applying this creation operator one times increases the number of particle at the ith position by 1. Okay. Now there is a phase factor here also, so we cannot neglect the phase factor. So if we write it like this, so this is the phase factor, and this term psi I, nu I, that is for I from 1 to, so let's say for 1 to let's say there is total I quantum states here, 1 from 1 to I. Okay. Then this goes from 0 to I minus 1, and this is nj. So this basically gives the sum of all particles. Okay. And this term, this minus 1 to the power nu I, this ensures the wave function is asymmetric to satisfy the Pauli exclusion principle. So this is how this creation operator acts on a wave function, and it generates an electron or gives rise to the number of the electrons or the particles, any particles at the ith state. So this this indicates on which quantum state it acts and gives rise to a, creates a particle there. Okay. Similarly, we can also, excuse me. So similarly, one can also introduce this annihilation operator. Annihilation operator. So this annihilation operator acts on a state. Let's say this state has one particle initially. So let's say this psi prime state is like that, like this initially. So n1, n2, and now in the ith state there is one particle. Now when this acts on this wave function, when this annihilation operator acts on this wave function, it reduces a particle at the ith state. Okay, so now this gives us psi I. Again this phase factor will be here and into, now it will get reduced by 1 and it will give you 0. So these are the basic definition of this creation operator and annihilation operator, and these two operators are very necessary, very important to define the BCS Hamiltonian or this BCS ground state wave function. Okay, so to exactly derive this BCS wave function or this gap equation, you will need this annihilation and creation operator very much. Okay, so that is why I started with this definition of annihilation creation operator, and next we will see what are the properties of this creation and annihilation operator. Okay, so properties of creation and annihilation operator. So these operators okay, so the rules are like this. So these operators follow this equation. So this is the anti-commutator bracket and this is, let's say I and j are the indices, and so this term will gives you delta ij. That means when I is equal to j, this is this when basically ci and ci dagger, this gives you 1. Otherwise if ci and this is other some k, then this will give you 0. Okay, so is there any question? Now this is the basic definition of the basic relation of this creation and annihilation operator, and we will now use these forms to find the number operator, to find the number operator that basically gives the number in at ith state. Okay, so if you add this operator on a wave function, so it will give you the number of the particle at the ith state. Okay, so it will give you the number of particle at ith state. So the number of particle in the ith state. Okay, so now we'll see how we can write this ni in terms of this ci, I mean this annihilation and creation operators. Okay, so in terms of ci and ci dagger, in terms of creation operator and this annihilation operator, this is creation and this is the annihilation operator. So how in terms of these two operators we can write this number operator. So for that, okay, so let's act. So we'll prove that ci dagger ci, this gives us the number operator. So let's say we have a wave function psi that is given by this in1 in2 dot. Okay, so this is our initial psi. Now we will act ci dagger ci on this side. Okay, so this term gives you when ci acts on this term, so this will give you minus 1 to the power nu I, because this is an annihilation operator, so it will annihilate the one electron that is existing right here in the ith state. Okay, so it will now annihilate this electron in the ith state, So we will now get only 0. We will get the electron in the I state will be 0. Okay. Now again we will operate this term here, creation operator, N1 into 0. So again this creation operator will create one electron at the ith state. So this will give you minus 1 to the power I N1 into 1. So we will get 1 into minus 1 to the power I 2, and this is our initial psi, and this term goes to 0. So you can see that when we add this term C dagger Ci on this wave function, it gives back a number 1. So what is this number? This number was initially the number of electrons at quantum state I. So it basically gives us Ni times I star. So that is how we can say that this Ci dagger Ci, this gives us the number of electrons. Okay. Now we will use this information to define the BCS Hamiltonian. Okay. So now we will start with the BCS Hamiltonian. And before that, if you have any question with this creation and annihilation operator, then you can ask me. So this Hamiltonian H, that basically consists of two terms. One term is the kinetic energy of the Cooper pair, and this is the potential energy of the Cooper pairs. Now, how can we write the kinetic energy in terms of this creation and annihilation operators? Okay, so every electron has an energy epsilon k or ek. We can now write. So let's say the electrons here. The electrons have energy ek, and there is one up electron and one down electron. Okay, we know that in a Cooper pair, there is always one k up electron and one minus k down electron. This is spin state, this is momentum. So for the spin up electron, so we can write the number operator. So let's say there are n number of electrons, spin up electron, and n number of spin down electrons. So to express the number of this spin up and spin down electrons, we have to write the number operator here, and we have seen that the number operator can be written in this term. So using this, we can write the Cooper pair Hamiltonian, the kinetic energy part of the Cooper pair Hamiltonian. So this is the number operator for this electron. We will sum up on the state k. This is the number operator for this electron. Okay. So we will sum over all the momentum state, and so basically this gives for the k up electrons, and this is the number operator for minus k down electron, and this is the energy for one electron. Okay, so this thus gives the total kinetic energy for k up and k down electrons. Okay, so thus we get the kinetic energy term of this BCS Hamiltonian. Kinetic energy of Cooper pairs. Now similarly, we can write the potential energy of the Cooper pairs. Okay, so the potential energy can be written as this: k prime b k k prime. This is the interacting potential. We have written this also. We have seen this before also. Okay, so then k r So what this term says, okay. So this is the interacting potential, but what this term says, okay. So this term says that we are creating one k up and k spin up particle, one k and spin up electron. We are creating one k and spin up electron, and one minus k and spin down electron. So we are basically creating a Cooper pair in and annihilating a k prime up electron and minus k prime down electron. So this initial state of this Cooper pair, so basically what happens that by interacting with a phonon, these Cooper pairs, electrons with k up, k prime up and minus k prime down, they scatter and they goes to this equation, this Cooper pair state, okay. So they are basically bound up bound in the influence of this interacting potential V k k prime. So this term gives basically says us this event, okay. So we have k prime up electron here and minus k prime down electron here. They go and interacts with the phonon or get scattered from this phonon. Then they ultimately gives us this electron, this Cooper pair. So k up and minus k down. So because these pairs are being created, these electrons are being created after this interaction, so we are using the creator operators for them, creation operators basically. And as these electrons are getting annihilated through this interaction, or they are getting annihilated through this scattering, we are using this annihilation operator for these two terms. Okay, so these two terms we are using the annihilation operator for these two electrons. So now, so this is our potential energy and this is our kinetic energy. So if we put back in our Hamiltonian, we get our BCS Hamiltonian like this. So CK number of order for K spin up state, spin up electron, number of order of minus K spin down electron. This is the kinetic energy plus the potential energy that is given by k prime, where summing over all the momentum states, V k prime the interaction potential, and we are creating k up and minus k down state for electrons, and at the same time we are annihilating k prime spin up electron and minus k prime spin down electron. So this is our BCS Hamiltonian now. So this is the starting point of BCS theory, okay. So I don't have much time left, so I will quickly go through all the other results that we can get using this equation, okay. So now we will also introduce the BCS wave function. This is our BCS Hamiltonian and we will use BCS wave function. So we will use a trial wave function. So this is kind of a trial wave function, this is kind of a guess, okay. So BCS introduced this wave function and this wave function is written as this. So this is our ground state. when there is no electron, all are 0, no Cooper pairs inside the system. Okay, so this is our ground state. Now we will act these operators on this state. Okay, so now we'll know what are these different terms. So it tells us. Okay, so this term tells us that so this is basically creating a k up state. Okay, so this is creating, okay, so there is a mistake here. So this is basically creating a Cooper pair. Okay, so with k spin up and minus k spin down state, 2 electrons. This term creates 2 electrons with one electron being k momentum and spin up, and minus k momentum and spin down for the other electron. So this basically generates a Cooper pair out of this ground state. Okay, and Vk tells us it's the probability that there is a Cooper pair exists. Okay, and so this term tells us that the probability that the Cooper pair there is a Cooper pair, and a Cooper pair state is basically occupied. So if this operates on this state, so it tells us, this Vk tells us the probability of this state being occupied, and similarly this mu k uk tells us that one state is empty. This tells us the probability that this state is empty. One state is empty, that means it's not occupied by a Cooper pair. Okay, so this is the probability of the state not being occupied, and this is the probability of the state being occupied. So this is the VCS wave function. Now what we will do, we will use this wave function. So our Hamiltonian okay, so our Hamiltonian was 2 part kinetic energy plus potential energy, and we now know our psi BCS ground state. So the next task will be to find the expectation value of this BCS Hamiltonian. I mean, find the energy of this Hamiltonian state by by finding the expectation value of this kinetic energy and this potential energy. Okay, so we'll use psi BCS here, write the kinetic energy term here, and this psi BCS. So, and then find the expectation value. Similarly, this psi BCS, potential energy, and then the expectation value. So then by doing the detailed calculation, you can find the total energy of this BCS Hamiltonian or this Cooper pair. Okay, so I will not do the explicit steps, and because that is also the part of your assignment. So you do this calculation by yourself, and you will find that by solving everything, you will find that ultimately we get the total Hamiltonian, I mean the expectation value of this BCS Hamiltonian, that's like 2 summation over k. This is energy of an electron. This comes from the expectation value of kinetic energy, and another term that is summation of k prime, v of k prime, vk star, uk, vk prime, uk prime star. Okay, and this comes from the expectation value of potential energy. So you will get the ultimate, doing all the internal steps you can reach to this equation, which gives you the expectation value of this VCS Hamiltonian. From here you can also see that this Vk also appears here. Okay, so the Vk tells you the probability amplitude of an electron or a Cooper pair, of a Cooper pair to exist. Okay, so so the Vk tells you the probability of an electron to exist. Okay, so this Vk gives you the total number of electrons, and by multiplying that with the exactly the electrons of this, the free energy Hamiltonian, this Ek is h square by k square by 2m minus EF. Okay, so this term is to note because we are doing the energy of this, we are considering the energy of these electrons, keeping this Fermi energy as a reference point. Okay, so this term is the energy of free energy of an electron with respect to the Fermi energy, and by multiplying this energy by the total number of electrons, because in a Cooper pair there are 2 electrons, and the probability of an electrons to exist or to occupy a particular quantum state, that is mod of Vk square. So these two terms gives you the total number of electrons, and this is the energy of one electron. So thus it gives you the total kinetic energy of the system. Similarly, it gives you the total potential energy of the system, where Vk and Uk star, this tells you, so this Vk and Uk star, that tells you that one Cooper pair is here, so Vk star tells you that this Cooper pair, this state is occupied by the electrons. So a Cooper pair with k and minus k down, this exists. At the same time, this Uk star, Uk prime star, tells you that these Cooper pair states are vacant, so they are not occupied by any electrons. So and then it goes to these two terms. This tells you that now the next step is k states. Uk, basically Uk gives you the probability of vacancy, and Vk tells you the probability of occupancy. So whenever there is Uk, it tells you that the k up and minus k down Cooper pair is vacant, and this Vk prime tells you that this k prime up and minus k prime down Cooper pair is occupied by electrons. So the total put in this term tells you that one Cooper pair, so initially there are, this is initial and this is final. So this tells you that initially there are 2 electrons, and one with k and spin up state and another with minus k and spin down state, and that interacts with a phonon, and they occupy this state, okay, this final state where one electron had k prime up and minus k prime down. So initially this state was vacant, and finally this state is vacant now because these electrons has gone from this state to this, occupy these states. Okay, so this potential energy terms tells us that thing only. So this is the energy expectation value of VCS Hamiltonian. So we got that this term. Now, now to find the equilibrium, I mean, this is the general equation, okay? So this is the general equation of expectation value of this HBCS. But it's not necessary that the electrons, the Cooper pair, basically, they always exist in this electron state, this energy state, because these energy states, they vary, that is a function of momentum, okay? Now we have to find what is the stable value, I mean, what is, so of course this electron will reside at that point only when this energy is minimum, okay? So we have to find the stable point of E, okay? So for that we have to minimize this EBCS with respect to some function of K, okay? So that will be our next aim, okay? So for that, one thing also to notice is that as UK mod of UK square gives you the probability of a state being vacant and VK square gives you the probability of a state being occupied. So this total term must have to be 1, okay? So now we will use this information to parameterize UK and VK, okay, in terms of a parameter theta k. So let's say is it not entered? Not okay. No. So we are here. So UK, we will parameterize UK. So this is like we have already done before. So UK can be parameterized at UK is equal to sine theta k and VK is equal to cos theta k, because cos square theta plus sin square theta is equal to 1. So we can parameterize by using UK is equal to this term and VK is equal to this term, and then we can use this information so to find the minimum, the to minimize this BCS energy, okay? So to the minimization condition is now then delta of EBCS, energy of BCS Hamiltonian, and by theta k. So theta k is now our parameter. So we have to find this equation, solution of this equation. This is the minimization condition of energy. Okay, so we know the expression of EBCS, all these two terms, kinetic energy and potential energy. So you do the in between steps, derive this EBCS, and take the derivative of EBCS with respect to this theta k, and also there is a lot of I think all these calculations are already done in the video, and so anyway it is not done also, it is I think your task to do, because I think it is also given in the assignment. So so I think you have to do these steps for yourself, it's not in the video. So do the initial step and initial stage, and then you can finally arrive at the at this, you can find by deriving, by doing this by taking this condition and by doing the initial stage, you can find two things. One thing, you can find the gap equation. So the gap equation is given by which I was telling before, that it is exactly like 2h cut omega t or minus 1 by v naught gf. So this is exactly equal to the binding energy of the system that we already derived in the previous questions. So you can find this gap equation, and another thing you can find is the evolution of Vk and Uk with respect to energy E. So I will just write the final result of Vk and Uk. What is the expression of Vk and Uk? So the Vk, the probability of a state being occupied, is given by this. And then Uk is given as this. Okay, so this, you can also find, doing this calculation, you can also find this to at this equation. Okay, you can find to this equation, find this to this equation, and okay. So one last thing we will do is, so we will plot this Vk and Uk with respect to E to see how it evolves with the energy. Okay, so now, so as I told you before that we are taking the energy of the electrons with respect to the Fermi energy, so we can write this energy electrons as this thing. Okay, so this is like 2 k square minus k square. Okay, so Vk square is then given by half 1 minus Ek minus Ef root over Ek square Ek minus Ef whole square plus, this is the gap. And okay, so now we equate, so when the electron is at Fermi energy, then Ek is equal to Ef. So putting this in this equation, we get that Vk square is equal to half. Okay. Also, when these electrons, so this is one thing, and when this electron Ek, that is equal to Ef minus delta, if you put this value again in this equation, you will find that Vk square is equal to 0.853, that is almost equal to 1. And when Ek is Ef plus delta, then this Vk square gives you 0.146, that is almost equal to 0. So all these things we are doing at T is equal to 0 Kelvin. This is a very important point to remember. So now if we plot this Vk with respect to energy E, then you will find, so when Ek, so let's say this is Ef, this is Ef minus delta, this is Ef plus delta. So when Ek is Ef plus delta, Ef minus delta is almost is equal to 1. So this goes to 1 value from 0 as soon as it reaches Ek minus delta. So Vk is now reduced, it also reduced and goes like this. So this point, as you know that as Ek is equal to Ef, Vk is equal to 1 by root 2. Now if we plot Vk square basically, so now this term at Ek is equal to Ef is half, so this is half, and at Ek is equal to Ef minus delta, so this value is what, 0.853, and when it is at Ef plus delta, it is equal to 0.146. Similarly you can do it for Uk also. So for Uk you will get the opposite thing, so it will start this point and go like this. Okay. So what this thing tells you, so this equation tells you that when this energy, when as soon as you reach this energy range, which is Ef minus delta, so initially all the electron states are filled, as we know at 0 Kelvin. Below the Fermi energy, all states are should be filled. Okay, but whenever we reach this range, the superconductivity Cooper pair starts forming, and that is why the single electron states, this starts to be vacant because the single electrons are making pair with other single electrons and they are forming a Cooper pair. So there now some vacant electron states are forming inside the superconductor. Okay, and also you can see that in this range the vacant states are now mode. Okay, and after some state it is all vacant states like in a normal metal. So you can see that the deviation from the normal metal is happening here. Ideally, in the case of a normal metal, all the electron states should be filled up below this Fermi energy. But as you see in the case of superconductor, as the electrons nearby this Fermi energy range, they are forming these Cooper pairs. So the single electron states are now being vacant because electrons from these states are making pairs with other electrons and they are forming a Cooper pair. So they are not now single electrons, they are Cooper pairs. So that is why the single electron states in these regions starts to be vacant, and there are some vacant states here. Okay, and you can see that also the UK. So this is for UK square. So you can see that initially all the states, so the probability of being vacant, because all the states are filled, so the probability of them being vacant is 0. But as soon as we reach at this range, so some states starts to be vacant because electrons from these states starts to make pair with other electrons. So some single electron state starts to be vacant. Okay, so that is why there is some finite probability of a vacant single electron state. So that is why this UK square starts to rise in this region. So this is all I wanted to share in this interaction session. So I hope these things can help you to solve the assignments of week 2. So that's the end of this interaction session. So thank you all for joining this session, and I will end the session here. Okay, so thank you all. Bye.
Thank you.